to
Okay, let me just test the volume, okay? I'm guessing it's audible at the back. Awesome. So yeah, when I was preparing for this talk, I was thinking, okay, how should I be positioning all this work we are doing here? And we have three big, let's say, words in this series. So AI, decentralized, and science. So all three are sort of 800-pound gorilla here. And what I'm going to do is first give some perspective on the decentralized and AI part, and then I'll bring it back to how we are actually applying it in the context of healthcare. So recently, I had this opportunity to co-author an article on Forbes, and the title was "What Does Super Powerful AI Looks Like?" So as we know, the term super is in vogue these days with super intelligence and Mark Zuckerberg stealing everyone from universe to build his super intelligence and so on. So the question is, what does this super intelligence is really going to look like? And I'm going to argue that we have been here before. So long time ago, when I was not born, apparently there was a huge craze about supercomputers. And people thought once we have them big enough, powerful enough, we will be able to solve all the scientific problems, we'll be able to simulate climate, we'll be able to, in fact, peek into the future. And turned out, yes, that has played out to a certain degree, but not that much. Something that created far more impact was this notion of useful computers. And why is that? One could argue it's with you, around you. It has a lot more context about you. And it also enables something which is connectivity. So with these useful computers, what you're also getting is interaction with others, communication with others, and that allows us to coordinate. And that's very important, especially like everyone here in the audience knows that there is some value to coordination, collaboration. So I'm going to connect this with another theme around this question posed by Yuval Noah Harari. Almost 10 years ago in his TED Talk, he asked this question, why humans run the world? And he gives this three models of species. So first is notion of scalability. So we really care about coordination at large scale. But turns out most species that are coordinating at large scale are actually not being flexible enough. So think of flock of birds or beehive. Each member of the species is assigned a task and they only operate in that zone. So they lack flexibility and they cannot change their role. They cannot overthrow a queen bee, suddenly establish a bee republic, for example. Another model we have is heterogeneity. So you think of pack of wolves. Here you have different members of the species taking on different roles, hunters, scouts, and so on. And also they can switch on the fly based on the problem they're trying to solve. However, the problem is they cannot operate at large scale. So you would have never heard of millions or even thousands of wolves hunting together. That does not happen just because this heterogeneous relationship is based on intimate bond and does not scale much. And turns out what makes humans very different from everyone else is this notion of these three things happening together: coordination, heterogeneity, scalability. And this is what Harari argues as the trilemma. Said usually you end up getting two rather than three. So this is going to be the main theme here, which is how do we get all three in one package? And that's the goal for really making this AI smarter and being able to solve tasks at a large scale. So what we are seeing in AI right now, what I'm calling as Great Divide. So this was actually a blog from one of the very popular researcher, Jason Wei. And he argues that whenever you have a task that can be verified, then you can make progress on that task very quickly. And you can train AI models almost in an autonomous manner where they're interacting with the environment and being able to self-improve because the task can be verified. So let's take a very concrete example. Imagine you're writing code. You do not need to generate a lot of data just because you can ask your LLM, AI, whatever, to write that code and make sure that code compiles. That's the step one. Most of the time, that thing itself we cannot do for other tasks. So think of answering a question such as, what is the best diet? So first of all, the question itself is a little bit problematic because perhaps there's no universal best diet. And then second is, how do we even verify this question? So this is the really like one of the problem that is creating this divide where AI is getting really good at certain kind of tasks, and at the same time, it's not progressing much on certain kind of tasks. So health falls in that category of tasks where verification is difficult, and hence bringing down through this bridge has been almost impossible, to be fair. There are some instances where actually it's making some progress. Think of drug discovery where you are predicting affinity or toxicity and so on. And you have some simulations also coupled with it where you can verify things. But other than that, not much. So a lot of times we argue about this notion, oh, we need more data, and that's true, but also we need environments where we can verify tasks. And once we hit that point, suddenly in many of these applications, not just health, we will see this notion of training in environment, self-improvement, and so on. And this is a problem we are targeting at Eon.Health. So I'm going to give this like a three-step formula, how we are approaching this problem. So first part comes in the notion of temporal learning. So you have a lot of time series data that you're generating if you're wearing a smartwatch, smart glass, and so on. And this time series data is not just a bunch of sequence of points. Actually, there's something interesting going on here. So when you have a sequence of data, it's also giving a sense of causality, where if one event happened before another event, then we know the other event might have some chances of being influenced by the previous event, but not the other way around. This idea is also widely used in training large language models today. It's called causal masking and so on. So this gives you a sense of correlation and causality. But then you also want to integrate different sources of data together. So we are generating massive amounts of data sets, and each of them are speaking their own language. And what you need is these bridges that can do translation across domains. So think of data sets like which are really high dimensional, like epigenetics or any multiomics for that matter. What's going on here is you have huge data sets. They carry a lot of information, but there's not much translation going on right now. So that's the second part. And then these two are amazing at individual level. They give already lots of insights. But we actually care about solving this problem at population scale, right? So that's where collective learning comes in. So here the idea is you have two models, and those are two extremes. So one extreme is classic randomized controlled trial kind of mindset. So you're taking a very big population, giving drug to one, giving placebo to another, seeing what works, what does not. Works great, but also has some serious limitations. One is, let's call it overgeneralization. So if you're averaging, which is what randomized controlled trials are doing, over a big population, then you're losing individual heterogeneity. And also, which leads to the problem that you might be missing out signals that are present, but of course, when you average over a whole population, you lost it. And the other way around, which is something might be actually not working or being toxic in a large, small part of the population, but because you're averaging over a big population, then you're ignoring those problems. The other extreme is n equals to 1. So let's just say I take just my own data, do every analysis on that. The problem here is there's a lot of spurious correlations, and there's a lot of time lag defects and so on. So what we actually need is this concept we have been working on for the last few years, is idea of collaborator selection, where you actually build clusters based on data sets and figure out who's similar to who. So we all have heard of this notion of digital twins, but with this, what becomes possible is digital sibling, digital cousins, and so on, where you figure out whose data is similar to you and then use that information to improve your outcome. So those are the three unifying factors, and we are doing orchestration on top of them. So time, space, and scale. And what that leads to is what we are thinking as positioning it like personal verifier from universal verifier. So when I showed you the slides where divide in AI, the divide is happening because you have this distinction between personal versus universal verification. So think of it as a lot of problems that are much more grounded in, let's say, physics have this notion of universal verification. But when it comes to personal verification, you actually care about data sets at an individual level or a cohort level where they're unified by some similarities in their biology. So something that runs on our platform is this EON app, where we collect a lot of variable data and make it possible for people to analyze their own data sets, but also be able to correlate with population level metrics. So for example, you could view your own individual time series data points. So this is actually all of my data coming from variables. And I can look at what things are correlated with what else. So is my heart rate variability impacting my sleep, or is my meal timing is impacting my other data sets or not? So very simple correlation analysis, but it shows you the power of being able to do this kind of really powerful data analysis, but at an individual level, and at the same time not operating in this your own n equals to 1 bubble, but actually getting signals from others' data sets as well. So what we have found out is actually that for different people, it could be different things. So for example, in my case, I found out my deep sleep is not impacted as much by my sleep timing, but actually not much impacted by my total sleep duration, but by bedtime much more. And this is just one example, but we have seen for different people is different correlations, different deviations that matter. So this really brings us to this almost concept of bridging this divide by creating these personal verifiers. And the way we anticipate in the next few years things are going to play out is we will be building environments, verifiers, for also the problems in health and other domains where you do not have this concept of universal verification. And once you bridge that divide, suddenly you see AI improving a lot on these kind of tasks, where you could ask questions like, what's the best diet? And yeah, that's it. Thank you.